Hello, everyone. This is our review session for Chapter 3 in this course, where we're learning about energy efficiency and energy conversion processes. So the real key of this chapter here is this one equation. And this is the one equation I will not provide in the exams or in the sheets because I want you to memorize it, because it is at the heart of this whole course. So useful energy out over total energy in is our energy efficiency. Now remember, the total energy in will always equal the total energy out, but many of it will be in forms that are not useful. So what that means is essentially we consume some primary energy source, and then a fraction of that total energy we're putting in goes to something that we want it to. Okay, and it's always going to be less. So whether we are moving the wheels on our car, we're trying to heat something up so that we can cook it, the total energy in, and that useful portion we're using to do some work, it will be less, okay? And so in each case, we will want to identify it because there will be many energy outputs, right? And that's the first law of thermodynamics, that the total energy in must always equal the total energy out. We cannot create or destroy energy. And that's what's really encompassed in this first bullet here. All the energy we put in does not come out in the desired form. No such thing. An important thing to note when using this equation is that the energies should have the same units. So you can't put joules in here and then say quads or BTUs or calories in here, because the unit conversions will give you strange values for this efficiency. So it's really important when you use this to make sure that the units in both the top and the bottom match. Okay. Another important note is that temperature of a substance is not a measure of its heat content. That's actually something that's energy related, but instead it's the average kinetic energy of the molecules in their motion, okay? One of the classic examples that was used long ago to try to identify this equation and to describe it and what started the Industrial Revolution is the heat engine, which is essentially a device that converts thermal energy into mechanical energy. So this comes up in our everyday lives. Well, it used to come up more, but as batteries and electrical energy conversion processes are coming in, maybe it'll come up a bit less as we turn off of fossil fuels. But still, there are a lot of classic examples we can see. Cars, for example, we take a gasoline, which is chemical energy. We then burn it to create thermal energy, and then that thermal energy ends up spinning the wheels on our car or the blades on our lawnmowers, right? And it also works on a larger scale for coal and natural gas power plants when they're moving a turbine. So these heat engines are described by the Carnot efficiency, which is a classic equation to tell us the limit of the absolute most energy we can get out of a thermal energy source, right? To use this equation properly, all the temperatures must be in Kelvin. This is really important when you're ever dividing temperatures. Kelvin should always be used. And then you can see some clear relations with Carnot efficiency that let you know how a heat engine can be more or less efficient. And a lot of that has to do with the temperatures that you're using, right? And so many of these principles are the key building blocks behind the workings of a power plant. And as we had mentioned before, right, this thermal energy to mechanical energy isn't really one step, but in fact, in a total power plant, there are many steps, right? So we have to go often from chemical energy to thermal energy to mechanical energy. And then from mechanical energy, we go to electrical energy, and that's what we use to power our laptops and keep the lights on. And the way that we account for that is we essentially use our energy efficiency equation, and we do that for each of those steps, and then we multiply the efficiency of those steps together, and that tells us our overall efficiency of the process, right? So what is the efficiency of going from chemical to thermal? Again, it will never be 100%, so some will be lost. And then from that useful thermal, how much is going into mechanical, and et cetera, okay? So please take some time to review each of these key points in this lecture, and good luck on the quiz. Okay,